Hello out there. Welcome today. So the lesson for today will be focusing on probability, but not just only probability. We'll split this into tree diagrams and contingency table. Okay? Remember out there at home, don't just observe only. You need a pen and paper, you need your calculator, where you'll scribble some of mathematics. That's the only way we study mathematics, not by observing. We practice, and we try problems. And I really encourage you to try some of the problems with us. Okay, let's see what we have today. So on the probability. So before we do that, what do you think, or have you ever thought about this? What is the likelihood, when I talk about probability or likelihood, just saying the same thing, of contracting a COVID-19 at the bar? Okay, so I'll encourage you to do a little bit of research and just check that, because usually at the bar, while you're drinking your coffee or whatever, you don't wear your mask. And the data does show that there's a higher chance of getting the COVID-19 if you go to a bar. Are we together? Hence, they actually put lots and lots of restrictions on that. So, but I'd like you to research, just check what is actually the chance of getting that, and compare it probably to school, okay? So you find there's actually a higher likelihood or probability. And how do they arrive to that probability and conclude that, yes, there's a higher chance? By collecting data. Collecting data and people who test positive. And they can see that the higher proportion who actually go out or do social distance are contracting the COVID-19. Fantastic. Let's see how we'll apply this in our life. So, but before we do that, I did indicate we'll look at probability, we'll look at tree diagram, and after looking at the tree diagram, we'll also look at the contingency table. Okay, let's start with tree diagrams. Some of the key words you need for your tree diagram. It's a sample space. What is a sample space? Okay. If I'm in a class with what? Chairs and table. Are we together? And I'm looking at that. So the sample space will be the numbers of chairs and table in the class, the total. Are we together? If I go in a class with boys and girls, I want to count how many boys and girls in that class will be how many boys and girls. Okay, so that'll be the sample space. And the possible outcome. So those will be actually the total, if you add, that is a total possible outcome. Are we all together? Okay. So very important, the probability to understand what is a sample space, understand the possible outcome. Okay. If I flip a coin, what is a possible outcome? I can get a tail, a head. Those are the two possible outcomes. But if I have a die, I have 6 possible outcomes which can come. 1, 2, 3, 4, 5, 6. If you have a fair die, you know there's 6 numbers there. So sample space and possible outcomes, almost kind of similar. Just the possible outcomes is what can come from rolling a die or flipping a coin. Okay. What is an event? We know an event. If I have a die, the probability that 1 occurs, that'll be an event. Are we together? Or 2, or 3, or 4. Also, if I have a coin, we can have a chance of getting tail or head. So those are the 2 possible outcomes which we can get from there. Some of the keywords, also independent and dependent events. Independent, can it come from being independent as a person, dependent, depends on something. Okay, so independent, let's look at dependent. Dependent will depend on the other outcome. Are we all together? So in probability, some outcomes are affected by other outcomes. Are we together? Let's look at flipping a coin. If I flip a coin, I get head or tail. Me getting head now, does it affect me, the next outcome? No, it's not. Are we all together? It's not affected by that. Okay, so we'll look at actual examples later when we look at dependent and independent events. Okay. Okay. So tree diagram are useful for organizing and visualizing different possible outcomes of a sequence of event. So each branch in the tree shows outcomes of an event along with the probability of that outcome. Okay? I'll show you with an example. For each possible outcome, the first event, we draw a line, okay? We write down the probability for that outcome and state the event if that outcome happened, okay? So if I have a coin, okay, I could have head or tail. So I will draw a line of that nature, are we together? Which is tail or head, okay? So it's an event, tail or head. That's the tree diagram, okay? So now there's an example using the tree diagram to determine the possible outcomes when a coin is tossed. We're together. So we're going to toss a coin. If we toss a coin, we can get what? Head or tail. And here we're assuming we're going to toss it twice. So you can draw a tree diagram tossing a coin once, twice, 3 times, 4 times. Okay? So we're going to look at twice. So we're looking at a coin. If we toss first time, we can get head or tail. Are we all together? If head occurred and we toss again, head does not affect the next outcome. Are we together? So we can still get head or tail. Are we together? We could have tossed the coin and the outcome was tail. If the outcome is tail and we toss again, we can still get what? Head or tail. Are we together? Then the possible outcomes, those are the possible outcomes. If you toss it twice, we could get head, head. Are we together? Head, tail, tail head, and head head. Are we together? So we have what? 4 possible outcomes. If we can toss what? A coin twice. So then the sample space, which is S, it will be HH for head head, head tail, tail head, and tail tail. Now, let's look at another tree diagram. But this tree diagram, we want to take a coin and a die, and we're going to throw those together simultaneously. And how do we draw a tree diagram? Okay, for that. So suppose a coin is tossed and a die is thrown. We can represent the possible outcomes in a tree diagram. So if a coin can give us what? Head or tail. Are we together? If a coin gives us head or tail, what about a die? A die can give us 6, 2, 3, 4, 5, 6. Are we together? And also it can give us, if we get tail, a die can give us 1, 2, 3, 4, 5, 6. Are we all together? So if we roll a die and a coin, we can get 6 and tail. Head or 7. Not 7. 7 is not a sample space because a die you have 1, 2, 6. Okay? Are we all together? Now the possible outcome can be head 1, which can occur, head 2, head 3, head 4, and head 5, head 6. And tail can come with 1, tail can come with 2, tail can come with 3, tail can come with 4, 5, or 6. Are we all together? Those will be the possible outcomes. So, independent event. Let's talk about independent event. So 2 successive events, A and B, are said to be independent if the outcome of the first do not influence the outcome of the second event. Are we together? Event A happens, then is followed by event B. Okay? Suppose that event A is tossing a coin. Event B is throwing a die. The chance of getting a particular number on a die, second event, will not be affected by the chance of the first getting head or tail, with the coin being first event. In general, in mathematics, we'll use this formula to test whether an event is statistically independent or whether we calculate probability given that they are independent. So the probability of A and B will be what? The probability of A multiplied by the probability of B, given they are independent. If they're not independent, you cannot apply that. Are we together? So the tree diagram we drew, that shows independent. Tossing a coin does not affect me getting a tail next. Are we together? Flipping a coin and a die, independent. Are we all together? Fantastic. When we come back now, we'll look at more and more tree diagram. Sit there and relax and keep working hard. We'll see you shortly after the break. Hello out there, welcome back. So we're still on tree diagram and we're focusing on probability, okay? So it's very useful to represent a probability situation using a tree diagram, especially if you have lots of outcome. I mean, if I flip a coin once, easy to deal with that. But if I flip it twice or three times, very useful to solve that problem using a tree diagram. Okay, so now let's look at a question where we're going to draw a tree diagram, and after drawing a tree diagram and solve some of the question. Okay, fantastic. So a tree diagram can be used to help solve problems involving both dependent and independent events. That's very important. It can solve independent and dependent events. So the following situation can be represented by a tree diagram. Let's read carefully. Tabo has 10 colored cubes in a bag. Okay, very important. 3 of those, I'm underlined, 3 of those cubes are red. Okay, if 3 are red, I mean 7 should be what? Blue. Because we have 10 cubes in a bag. Are we together? And what we know is that 3 are red and 7s are blue. Fantastic. What does Tabo do? He removes a cube at random from the bag and note the color before replacing it. Very important, before replacing it. So what he does, we have 10 cubes in a bag. What Tabo does, put your hands in a bag, replace, take out a cube, and you look at the color, and you'll put it back. So with replacement. So he replaced it back. Okay? And I want you to think about also, what if he doesn't replace? What happens? So he's replacing now. Okay. Will it change probabilities and stuff? Will this change the tree diagram? How would it look like? Okay. So let's see. Then he chooses the second cube at random. Use the tree diagram to determine the probability of all different outcomes occurring. Interesting. It's not easier than a coin, because a coin, my outcome is tail or head. We together. Now we have a situation, we have a bag with 10 balls inside, and we know that, how many of them? 3 are red and 7 are blue. Take a ball, put it back, take a ball, put it back. Draw the tree diagram and show the possible outcomes. What is an outcome? We could get blue. Put it back. We could get blue again. Put it back. Or we can try. We get red, we put it back, we get blue. Those are the outcomes we can have. Let's see how a tree diagram looks like. Okay. So tower has 10. He has 10 colored cubes in the back. Very important, 3 of the cubes are red and 7 blue. So we have 3 red, okay, and 7 blue for blue. He removes the cubes at random from the back and note the color and replacing it. Very important, you replace. Then he chooses the second cubes at random. This means the 2 events are independent. Why do we say they're independent? Me getting red first will not affect the chance of me getting blue the second. Why do you think they're independent here? Any idea? Why is this independent? Because I'm replacing back. The sample space will stay the same. Are we together? Because I'll still have 10. If I draw blue, I have blue, I see blue, I put it back, I'm back to the original setup, which is 10 balls in a bag. But now if I don't replace, and I put it away, that's a different scenario. Because now I won't have 10 balls anymore, I'll have 9 balls altogether. Okay, so this is an independent event because we are replacing. So let's see what we get. So the first choice will have a red. There's a red. What is the chance of getting a red? How many red balls in the bag? We have 3 red balls. What is the sample space? 10. So the probability will be what? 3 out of 10, which is 0.3 or 30%. Okay, so this is what we get. We can get red or blue. The probability of red is 3 out of 10, and the probability of blue is 7 out of 10. So this is your tree diagram. You put a line like that and a line like that. That's the first. Because the probability of getting red is 3 out of 10, of getting blue, 7 out of 10. Why 7? Because there are 7 blue balls in the bag. And there are 3 red balls. This is what we do for the first time. And how many times we do this twice, it states. He then chooses a second cube at random. Then we're going to choose another one. We replace and we do again. What do we get? For second choice, we can still get red or blue. Doesn't matter. I'm getting red. I'm getting red for the first time, but I replace it. I can still get red. Or I can get blue. What about the probabilities? Will the probability change? No. Because I'm replacing it back, I still have 10. I still have 3 blue, 3 red. I still have 7 blue. Nothing has changed because I'm replacing it. So what it means, and for the second part also, if I get blue and replace it, if I do it the second time, I can still get red or blue. I can get red or blue, and one of the probabilities, the probability of red is 3 out of 10, and the probability of getting blue will give us what? 7 out of 10. And what about the probability of red? Still the same, which is 3 out of 10, and the probability of blue also is still 7 out of 10. Are we all together? I'd like you to look at something here. What does this number plus that number add up to? Can you see that? 3 out of 10 plus 7 out of 10. We call those the branches of the tree. 3 out of 10 plus 7 out of 10. Can you see that add up to 1? Yes. Let's go to the second branch. Again, 3 out of 10 plus 7 out of 10. What do we get? We get 1. Also here, 3 out of 10 plus 7 out of 10, we get 1. That will always get up to 1. Are we all together? Okay. So let's look at the possible outcomes. Red, red, we'll get the probability of red being red. We have to multiply the branches. 3 out of 10 multiplied by 3 out of 10. So the probability, P means the probability of getting red and red is 3 out of 10 times 3 out of 10, which is what? 9 out of 100, which is 9%. What is the chance of getting red twice? The same question. Okay. Now let's look at what is the chance of getting red followed by blue. So it implies if you get red followed by blue, this is what we'll get. We'll get red followed by blue. What is the probability of red? Red is still 3 out of 10, then followed by blue. What will that give us? 3 out of 10, agreed? Times 7 out of 10, which is 21 over 100. Fantastic. Then the likelihood, probability of getting blue followed by red. The chance of getting blue followed by red will give us 7 out of 10, because we're getting blue, then red, which will give us what? Probability of blue, then red. What is the probability of getting blue? 7 out of 10 of getting red, 3 out of 10. We get 21 over 100, which is 21%. The chance of getting blue, blue. It what? 7 out of 10 multiplied by 7 over 10, which is what? Which is 49 over 100. Just 49%. Okay, fantastic. Now, let's look at this. This is the tree diagram complete. We drew a tree diagram, which is our first choice there, second choice there. What does this represent? So the end and the first level of the branches shows the different outcomes. Are we all together? Then the probabilities of each event are shown along the arm of each branch, and they add up to 1. That adds up to 1. We all together. And lastly, because the events are independent, the probabilities must be multiplied along each arm. You multiply that and that to get the actual probability. For now, we'll take a short break and we'll see you shortly. Welcome back again. We're still looking on probabilities and we're focusing on tree diagram. Okay. Now, we have a problem for you and we'd like you to try with us together and let's push together and let's see what we get. So here, still a tree diagram, okay? Nothing about whether it's independent or dependent. So what do we know is a Tabo, okay? Tabo and Peter, they run a race and play a tennis match. So they run a race and play a tennis match. So the probability that Peter wins a race is 0.4. So we give it the actual probability. The probability that Peter wins a race is 0.4. 0.4 is 40%. And the probability that Tabo wins a tennis is 0.7. So that is given on a tree diagram. So we have Peter wins, Tabo wins. What are you talking about? This part, we're talking about a race. What is the chance that Peter wins a race? It's what? 0.4. If the chance that Peter will win a race is 0.4, what is the chance of Tabo winning a race? We know that the branches add up to 1 because we have 0.4. 0.4 plus what to give us 1? That will be 0.6. So we can actually calculate the probability of a known line on a tree diagram branch using the other, because we know that and that add up to 1. Are you all together? Great. So the first question is, complete the tree diagram given. So there's the tree diagram given to us. We need to put in something there, and there, and there. Then use the tree diagram to calculate. So we have to use it to calculate what? The probability that Peter wins both events. What do we mean events? We're talking about what? Tennis and race. Then the probability that Thabo loses the race but wins a tennis match. Okay, loses a race but wins a tennis match. Okay. So firstly, if I can complete my tree diagram, I'm able to calculate the actual probability. So let's aim by completing that first. So firstly, we knew that this was what? 0.4, that will add up to 0.6, because the sum of that and that will give us 1. And we had Thabo 0.7 there. Then this part for Peter will be 0.3, because 0.7 plus what to give us 1 is 0.3. And we get Thabo wins 0.7 there and 0.3. Then let's look at the possible outcomes, because if we have a tree diagram, we can just trace the possible outcomes. So what are the possible outcomes? The possible outcome will be here. Peter wins, there is, because it's Peter wins, and wins a race. Are we together? Because this we're talking about a race in the first branch, and we're talking about a tennis in the second branch. So the probability that Peter wins race and tennis, it will be 0.4 times 0.3. 0.4 times 0.3, which will give us 0.12. Now, the probability that Thabo loses a race, are we together? Loses a race and wins a tennis will give us what? 0.4, because he loses a race, which is what? 0.4, where's 0.4? 0.4 multiplied by 0.7. There's Thabo. Okay? Then the probability that Thabo wins race and loses tennis, okay? Thabo wins a race, 0.6. We're looking at that branch, 0.6 multiplied by 0.3. Okay? So we just multiply your branches. Then Thabo wins a race and tennis. Race and tennis is 0.6 times 0.7, which is that branch multiplied by that branch. Okay? So this is what we get. Okay, our probability. So the probability that Peter wins both events. So Peter wins both events, we can see what we're getting here. Okay? Peter wins a race and tennis, we get 0.12. 0.12, which is 12%. That's the chance that Peter will win both events. But what about the probability that Thabo loses a race but wins tennis? Okay, Thabo, that will be what? Thabo loses a race and wins tennis. It will be 0.4 times 0.7, which is 28% or 0.8. We all together. So if I have my tree diagram, I'm able to calculate whatever question that comes out in terms of the probability by just using my branches. Okay. Now, let's look at what is dependent event. Okay. So two successive events are said to be dependent if the outcome of the first have an influence on the outcome of the second event. Very important. Are we together? the outcome of the first have an influence on the other outcome. Those are dependent events. Okay, let's look at what that looks like. So Jabula has 10 colored cubes in a bag. 3 of the cubes are red. So what do we know is that 3 of the cubes are red and 7 are blue. So 3 red, 7 blue. We all together? He removes a cube at random from the bag and note the color, but does not replace it. Very, very important. Put his hands in the bag. Note the color, does not replace it. If I don't replace, I have 10 cubes in my bag. I get one color. I don't replace it. What changes? What happens? Now I have 9 balls. If I have 9 balls now because 1 ball gone, what does that affect? My total sample space is no longer 10, it's 9. And I can do the same thing again, remove another one. If I remove another one now, how many balls left in the bag? 8. So it affects the sample space. It will affect the probability of the next event occurring. How will this tree diagram look like? Okay, let's see. So let's record the information in a tree diagram. So first choice, we have red and blue. So the probability of red occurring is 3 out of 10. Why? We have 3 red. So it'll be 3 out of 10. And what about the probability of what? Of blue? It'll be, are we together? 7 out of 10. Because initially, we still have 10 balls, nothing. We have 3 red, 7 blue. What is the probability of getting red? 3 out of 10. What is the probability of getting blue? 7 out of 10. Then you draw our tree diagram. This is what we get. You draw your line. This is red. But now, we don't replace it back. What will change now? Will the probability still stay 3 out of 10? No. Because we don't have 10 balls anymore. Now, if we took red, we take red outside. We don't replace it. We have 9 balls, but how many red? Initially, we had how many red? 3 red. Now we'll be left with 2 red. Are we all together? Now, for blue, we had 7 blue balls. What if I take blue? I put it aside. What changes? I don't have 10 balls anymore. I have 9. But how many blues? 6 blues now. Because I've not replaced it back. Are we together? So it affects the branches of the probabilities and the actual probability. So let's see now. The chance of getting red will be, so we can get red, blue, and blue, red. Of getting red now will be 2 out of 9 because there's 2 blues now because red is out and the size now is 9. Probability of getting blue. Blue will still be what? We'll still have 7 blues inside because we have not touched any blue. But how many totals? 9. We'll have 7 out of 9. This is what we'll get there. And if we had blue for the first time, let's say we get blue, and then we get red. What changes? We'll get 3 out of 9 because there'll still be 3 reds. But blue out, now we don't have total of 10. Agreed? We have a total of 9. And what about blue? What does this mean? Blue is out. 1 blue out. We have initially 7 blues. Now we have 6 blues. And the total in that bag is no longer 10. It's what? 9. Then we'll have what? 6 out of 9. This is what we get. The probability of getting red, you just multiply that branch and multiply that branch, which is what? 3 out of 10 times 2 out of 9. Similarly, blue, red, multiply together. And what about blue, red again? It or still blue-red, which is 7 out of 10 times 3 out of 9. We multiply, you get 21 over 90. The probability of getting blue, that is the line, and this is what you get all together. So this is what it means. These are all your possible outcomes. A replacement and no replacement. Remember, when you don't replace it back, it changes the sample space and it reduces the other colors. Are we all together? So the probability is really affected. The probability of one event occurring affects the other. Okay, guys, fantastic. We'll take a short break, and when we come back after the short break, we'll look at more problems. And we encourage you to keep working hard and to push hard. We will definitely see you shortly. Hello there, welcome back once again. Now we're still in probability, but what are you looking at a probability? We're going to look at contingency table. Have you heard of what contingency table means? It's another way of representing probabilities, what is happening, okay? And you have probably seen that, okay? With a report, when they write a report or summary, it will be kind of a table. But we call those contingency table. But ask yourself, why not say table? Why do you say contingency table? Yeah, we call them contingency table in statistics. Let's see what it looks like and let's define it. So, another way of representing possible outcomes of an experiment is using two-ways contingency table. So two-ways contingency table are tools of keeping records of counts or percentage and probability problems, okay? You probably have seen that, yeah. Reports, especially the COVID report, they put tables. That's another example of contingency table. So two-ways contingency table are especially helpful for figuring out whether an event is dependent or independent. Do you remember independent or dependent? Are we together? Does it mean if I don't social distance, will I get COVID-19? Is that dependent or independent? Yes, if you don't, the chance of you getting COVID-19 is high. By staying at home and social distancing, doesn't mean I'll get COVID-19. It doesn't mean I won't get it. But the probability, staying at home, yes, can affect the chance of me getting it. Are you all together? That's how one uses those statistical independent. They'll collect data and study and come to a conclusion. Fantastic. So let's look at a table, a two-way contingency table. The table below shows the results of testing two different treatments on 240 fruit trees which have a disease causing trees to die, okay? So what it means, they tested trees, 240 trees, because they found that some of the trees are actually dying because of certain disease. We don't have the money or the finances to test each and every tree. What do? A sample. A sample of 240. We test on 240. And from 240, we can draw a conclusion. There's no way also, if you look at even COVID-19, to test each and every one in the country. You do with a sample, from a sample of 240, then we can draw some conclusion. Yes, the bigger the sample, the better your conclusion, or the reliable is that conclusion. Okay, so treatment A involves a careful removal of the infected branches. Okay, that's the treatment A. Treatment B involves removing infected branches as well as spraying the tree with a chemical. So you're going to remove it and spray with some chemical. All together. So let's see our table. What does our table mean? So our table shows treatment A and treatment B. Then, number of trees that die within 4 years. How many trees dies within 4 years? Then also, number of trees that live beyond 4 years. Are we all together? We can see treatment A there, we have 70. Numbers of trees that dies within 4 years. Numbers of trees that lives beyond 4 years is 50. And treatment B, nothing recorded. But what do we have? We have the total here. What is the total? The total is actually that number plus that number. Treatment A plus treatment B. You can see that, which is 90. So we can actually find that number, which should be what? 20. Because 70 plus something to give us 90. What is that number? 20. Also here, we have 50 plus something to give us 150. What must we add there? Surely we should be adding 100. We're adding 100. Then what do we get the totals here? We can get the totals by completing the table. 70 plus 50 will give us 120. And here we'll add the two numbers there to give us that total. Okay, let's see. What do we get? So the first thing is you have a contingency table. Yes, someone will go research, but you might find that the contingency table is incomplete. Yes, I can complete it. How do we complete this? So let's see. Number one, we are going to fill in the missing values on the table, which you've done so far. After that, calculate what is the probability that a tree receive treatment B. Because remember, we have two treatments, A and B. So at random, any tree can receive any treatment, A or B. Are we all together? So what is the probability that a tree receive treatment B? Are we all together? What is the probability that the tree will live beyond 4 years? And our fourth problem, what is the probability that the tree is given treatment B and lives beyond 4 years? Then our last question, are a tree given treatment B and living beyond 4 years independent events? Justify your answer with a calculation. Okay, let's see. So we complete our table. If we complete our table, this is what we get. We have 20 there, we have 100 there, and we just add rows. We add the first row, we get 120, we get 120 also here. Together 240, we add 120 plus 120. We get 240. So if you completed your table, sometimes the table is incomplete, you can complete it. And if you have a complete table, you can start by calculation. Let's see. Now, the question now is, the probability that we receive treatment B, a tree receive treatment B, that will be what? Receive treatment B, how many in treatment B? Over the total numbers of trees all together. So treatment for B is 120, which is conducted on trees, B. The total altogether is 240. So we go what? 120 divided by 240. We get a half, which is 0.5, 50% altogether. And the second question, what is the probability that the tree will live beyond 4 years? Live beyond 4 years, we'll have to look at what? Notation important. Probability lives beyond 4 years. So live beyond 4 years over the total altogether. Live beyond 4 years. Where is that? The numbers of trees that lives more than 4 years. It's on our table is there. What? It's 150. That's the total. Over what? The whole total, which is 240. And simplify that, we get 5/8. You can leave your answer as a fraction, or you can write decimal or percentage. Okay? Then problem 4. What is the probability that a tree is given treatment B and lives beyond 4 years? We want to give treatment B, but live beyond 4 years. So this will be what? The probability given treatment B and lives beyond 4 years. So this will be the number given what? Treatment B and live beyond 4 years, which is what? Number given treatment B, there's treatment B, living beyond 4 years, that will be what? 100. That's the number there. Can you see that? That's the intersection between treatment B and living beyond 4 years. And we divide by the total, which is 240. And we get 5 out of 12. Okay. Then our last problem is, are a tree given treatment B and living beyond 4 years, independent event? Justify your answer. To show that two events are independent, you have to show that the probability of A and B is the same as the probability of A multiplied by B. So what we have to show here is that the probability of tree given treatment B and living beyond 4 years is the same as the probability of given treatment B multiplied by the probability of tree living beyond 4 years. Let's see what it looks like. So what you're going to do is this. The probability of tree given treatment B and living beyond 4 years, we've calculated some of them here. It was 100 over 240. Then the probability of tree given treatment B, we're together. Tree given treatment B, where's treatment B? There's treatment B there, which is 120 over 240, which we have it there. A tree lives beyond 4 years. A tree lives beyond 4 years. How many? It's 150 over what? 240 altogether. And we multiply this, we get that this is 5 over 16. But we can see that 5 over 16 is not the same as 5 over 12. You have to state that. 5 over 12 is not the same as 5 over 16. Why? Therefore, the two events are not independent. We just had to show that event A and B is not equal to probability of A times B. Are we together? Then we conclude this is not independent. Okay. So let's look at our summary. So we've looked at tree diagrams. So tree diagrams, very important. You have to look at what? Replacement and without replacement. And that will affect your sample space if you replace or you replace. Are we together? If I replace, if I have 10 balls, we'll still 10 balls inside. If I don't replace, the size gets reduced. We've looked at independent event, independent, and contingency table. Okay. Cheers, guys. This is bye from us, and we hope that you enjoyed, and we hope to see you soon.